Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Quick note before we begin, the Finding Genius Foundation, as part of the Finding Genius podcast, has recently completed a book about understanding viruses. So the creation of this book was to interview 100 virologists, ask them a lot of deep, difficult questions, take the most difficult questions, and then re-interview the top 25 or so and ask them the hardest questions I could think of. And we compiled that all into a book. So you'll see question and 4 or 5 experts' answers. Question, 4 or 5 experts' answers. There's about 30 questions in the book. I think it's a great read for the layperson and for the researcher. It talks about a lot of speculation in the world of viruses, such as are they alive or not, and why is it important? Why do viruses go latent or hidden or ineffective or sit in a person or an animal or another creature for weeks, months, years, and then suddenly become virulent and affect that person? So there's a lot of really provocative questions in the book. It's now on Amazon. So if you go to Amazon and type in Finding Genius, you'll see the book on viruses. It's also on Kindle. If you want to go and order it now, you can do so again by going to Amazon or Kindle, or go to findinggeniusfoundation.org and go to publications. There's an opportunity as well to get the transcripts of all the interviews and to hear the original interviews themselves. If we had put them all together, the book would be about 1,000 pages, but we condensed them down to make it juicy and concise and tight and very interesting. So I hope you'll check out the book. We're now working on one about cancer, but this is going to be our goal is 3 times a year to come out with these masterclass books that I think will inspire new scientific research, and I hope you'll check it out. Thank you. Hello, this is Richard Jacobs with the Finding Genius podcast, now part of the Finding Genius Foundation. Today I have Chiara Marletto. She's a research fellow working at the physics department, part of University of Oxford. And within Wolfson, she's an active member of the Quantum Cluster and of the New Frontiers Quantum Hub. So we're going to talk about her research, the quantum theory of computation. So, Chiara, thank you for coming.
Yeah, thank you, Richard, for inviting me.
Yeah, I guess in plain speak, what's your research about?
So my research is within the field of quantum computation, but it's actually looking at developing it further. So in a way, quantum computing is this field that emerged in the 80s and has now become very established. And it's about trying to, on the one hand, understand from the theoretical point of view how a machine that uses quantum effects to work could possibly outperform the classical computers that we currently are using. And on the other hand, is also about trying to build this machine, the universal quantum computer. And so it's also kind of an engineering enterprise. But my work is more on the theoretical side, and it's looking at developing a theory that goes beyond the quantum theory of computation and describes machines that can be more general than computers. So they're not just capable of performing computations, but they can perform any physical transformation that is allowed by a certain law of physics. And these machines are called constructors, and they were introduced by John von Neumann, who is a mathematician and a physicist, back in the 50s. And since then, they had not been really developed. But I think now that we have the strong support of this theory that we developed with the quantum theory of computation, we can tackle this issue that von Neumann already pointed out then and try to really understand the foundations of these new generation of programmable machines. So that's the general context in which I'm working.
So how many different methods are there to make a quantum computer? I've heard there's superconducting loops, and what are the main methods by which people are trying to make quantum computers?
So there are a number of them. I think there are different platforms that have been tried. I think there are, as you said, superconducting qubits. There are a number of other solid state implementations. And there are also technologies that mix various different variety of these platforms. And I think the key thing that makes them all similar in one way is that they're all trying to implement this general scheme that was proposed, as I said, in the 80s, where the idea was that it didn't really, so at the time when this was proposed, is that it wouldn't really matter what particular platform one were to choose. What mattered is that the key idea there was the fact that, all of these different ways of realizing a qubit, which is like the basic unit of quantum information, are all the same from the theoretical point of view, because they all have the same computational power. Now, of course, this was the theoretical way of describing things. And, that was very interesting from the Foundation's point of view, from, the idea of understanding better how quantum theory can power quantum computation and so on. But then when it came to actually realizing these various algorithms that were proposed and then trying to realize the ultimate goal, which is this universal quantum computer, it became clear that some of these platforms are actually better than others. And I think currently there are a number of these that are being tried. And some of the companies that are developing these technologies are actually also very secretive about it. So we don't know all the details in a sense. There are also universities that are trying to develop some maybe smaller scale quantum computers. And so there is a kind of worldwide effort towards, delivering this holy grail of the universal quantum computer. And my understanding is that a number of these possible implementations will actually ultimately work.
Well, what are some of the difficulties with quantum computing? I've heard there's noise, there's errors, they have to be run, extremely cold. Like, what are the various factors that go into making the quantum computer or qubits that work? And what are some of the challenges?
Yes, so I think, again, from the point of view of the implementation, there are some very subtle details that, only engineers and physicists that are working exactly on the implementation would know about. But in general, I think the main difficulty, as you said, is the noise. So you have to understand that the fact that the qubit can perform a computation in the way that's required is not, so it's on paper can look very simple, but actually when it comes to making sure that even a single qubit performs a computation in an accurate way, one has to make sure that it's isolated from a number of potential noise sources that exist in the environment. And the thing gets worse when, of course, we have a number of these qubits. Currently, I think there is this magic number that's been mentioned a number of times. So there's 50 qubits that can currently work currently in some of these quantum computing platforms. So 50 sounds like a very small number of qubits if you compare it to the number of bits that are available inside classical computers. And the problem with noise is that it becomes worse and worse as you add more and more qubits. So I think that's one major challenge, is to implement error correction on a number of qubits that are implementing a quantum computation. And this means to counteract the noise, or to also isolate the qubits in such a way that the noise is reduced. And I think there are a number of ways in which this can be done. I think engineers are really trying to implement a number of different ways of approaching this problem. But
do you have to isolate each qubit alone, or is there a certain number of qubits that you can group together, but beyond that, some certain number you can't?
Yes, I think the idea is that you have to do it collectively, because ultimately to encode enough information in order to perform a computation that can, for example, implement certain algorithms to, for example, to factor a number, you do need sufficient number of qubits. And then you would want to isolate all of them in a way from the environment. And the trick there is that either you can, so the first thing to do is really to reduce the noise as much as you can, but then there are also techniques of error correction that are designed in order to correct the computation once it's performed. And the error could be either in the way the qubits are prepared or in the way the computation is implemented on these qubits.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
And so both the gates, so the transformations that perform the specific computation are corrected, or the qubits that are kind of provided as input to the quantum computer. So I think there are difficulties in both these places.
How sensitive is the environment of a quantum computer? Again, so far as I know, they have to be extremely cold. How cold is it? If there's a passing truck nearby outside the lab, or a train or stray electrical equipment, like how sensitive are these systems? How isolated do they have to be?
Again, I think this depends on the particular implementation, and you can ask about these details to people who are actually working directly on these applications in a way. But I think in general the sensitivity is very high. I mean, if you think even just there are some labs where people are trying to make certain objects behave in a quantum mechanical way, not many of them, just a single molecule, for example. And I think even there has to be a kind of a huge amount of isolation. So in this sense, I think this is why this technology is not ready to be made into a commercial form, because it really requires still a number of devices that are really only existing within the specialized labs. So in this sense, I think we're not yet at the moment where things are portable. If we're talking about quantum computer with a range of possibilities, but we are trying to get there. And again, there's also the fact that most of these companies are currently running, racing towards getting better and better special purpose quantum computers and ultimately a universal quantum computer. Some of these companies are actually working in a kind of very secretive way. So, at some point we might be surprised and they might come up with something really cool.
But in the theoretical angle, what are you working on specifically? What are you trying to understand and model?
So, as I said, my interest is in understanding what happens next. So the theory of quantum computation is based on the fact that there are a number of interactions in the universe that are ruled by quantum theory. And the idea here is to try to imagine what would happen to the whole of the idea of the quantum computer if quantum theory turned out to be modified or changed. So you have to think quantum theory is this explanation that was proposed almost a century ago to explain microscopic systems and the way they behave in a way that's better than what, say, Newton's laws did. The theory has turned out to be very useful for computations. However, we know that the quantum theory will have to change because it's not compatible with the other most fundamental explanation that we have, which is general relativity. And we've had these two theories for now about a century, and they work very well in their respective domains. But when you put them together, you see a number of clashes. And so my work is into thinking what would happen, to the theory of quantum computation if we were to remove some of the properties of quantum theory, imagining a potential successor of quantum theory. So is there a way of...
If you like this podcast, Please click the link in the description to subscribe and review us on iTunes.
Preserving all of these features of, say, the universal quantum computer, even if you don't have the whole of quantum theory at your disposal. And so this is what constructor theory, which is this generalization of the quantum theory of computation I'm working on, is all about. And is also about this other way in which you can generalize the quantum theory of computation, because it's kind of studying the next generation of computing machines that can come after the universal quantum computer, which are these constructors that I mentioned earlier. So I think
what does that mean? What are the constructors? Like, can you explain the theory a little bit?
Yes. So a constructor is a generalization of a computer. So a computer is an object that can be programmed to perform computations that are allowed by the laws of physics. And we have a classical computer, a classical Turing machine, and then we have a quantum Turing machine, and so on. Now, there are other types of transformations that a programmable machine can perform. And for example, you can think of thermodynamic transformations. So, for example, cooling kind of Coke from one temperature to another temperature, or you can think of a chemical reaction, or you can think of, for example, the task of self-reproducing, which is a task that is chief for biological systems. So a cell is capable of self-reproduction and so on. And while a computer can simulate these behaviors but can't directly perform these tasks, a constructor can be programmed to perform a range of these tasks. And the universal constructor, just like the universal computer, is a constructor that can perform all tasks that are physically allowed. And the reason why von Neumann proposed it and suggested that these machines should exist is that he had noticed that the universal computer, the universal Turing machine, was lacking the ability of performing some of these more general tasks, such as, for example, self-reproduction. And von Neumann wanted something that could emulate fully, for example, the ability of a living being. And so the universal constructor should, among other things, be capable of performing that. So the theory I'm developing is both a generalization of the quantum theory of computation, both in the sense that it kind of underlies constructors. So it should help us understand how they work and how to program them and how to ultimately build the universal constructor. And at the same time, it's also looking to trying to remove some of the assumptions in the quantum theory of computation so that it doesn't rely anymore so heavily on quantum theory, because this theory may at some point stop applying. So this is the kind of focus of my current research.
Okay. I mean, if quantum computers are so sensitive, then how are we ever supposed to make them where they're robust enough that they replicate themselves, or they take on all these additional functionality? I mean, it seems like impossible just to get them to work in any hospitable environment, or, in the absence of massive shielding right now.
Oh, yes, this is very far in the future, technologically speaking. I think, as I said, so the idea of the universal quantum computer was proposed in the 80s. And, down the line, we are a few years down the line since then. And I think we're still kind of trying to build this machine. So from a technological point of view, these things take a lot of time. And so in some sense, this type of development I'm looking at is preparing the ground for the technology of, maybe our future in 50 years or more. And I think this is what theoretical physics really is about, in the sense that for example, when Turing invented his scheme for a Turing machine, he couldn't foresee that this would then lead to, for example, the introduction of personal computers and the computers that we use currently nowadays, and then all of the IT revolution that came with that. Because he wasn't interested in trying to develop that at the time. He was really into understanding the foundations of computation and so on. So I think the kind of research that I'm doing and the kind of research that also led to, for example, the theory of computation in the first place, wasn't immediately directed to applications, although actually they ended up coming out of it. It's more directed towards understanding the foundations of, for example, in this case, quantum theory, or In the case of Turing, it was the theory of computation. In the case of von Neumann, was understanding the foundations of how, life works and how programmable machines in general works and what, their existence means for the regularities that we have in nature, et cetera, et cetera. So I think the focus that I have is very theoretical and more directed towards foundations rather than technology. But in this, I think in a way there's an interesting interplay here between the very theoretical abstract research and then what can come out of it in terms of technological developments a few years down the line.
Are you privy to any of the quantum computing methods that seem to be working the best right now? I know there's a lot of hidden stuff, but from what you've observed, which type of quantum computer seems to be the most workable or likely to be commercialized? I mean,
there are a number of things that you use in theoretical physics research. And so there are qubits that you can realize in laboratories inside universities. For example, here at Oxford, there are a number of such qubits. So there are NMR qubits, there are superconducting qubits, cold atoms, and so on. But I think which one of these actually works best and why for the specific purpose of creating a commercializable universal quantum computer, it's a question for those people who are actually working on building one of these things. And I can speculate, but I think it's maybe best that they give you an answer. Okay, well, very good. Well, Chiara, what's the best way for people to see more about your work? Where can they go? I think there is a website, constructortheory.org, and there is a book which is kind of just come out last week in the UK and the US, I think, entitled The Science of Ken and Kant, where I'm describing these developments beyond quantum computation. And lots of talks and interviews on the internet, I think, that you can find by Googling my name. Okay, very good. Well, Chiara, thank you for coming on the podcast. I appreciate it. Yeah, great talking. Thank you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.